Hello everyone and welcome to ETEC221 lectures. Today's lecture is lecture 5. We will talk about oscillators, and that's the first part. Oscillator is an electronic circuit that generates a periodic waveform on its output without an external signal source. It is used to convert DC to AC. However, in this concept, students should not mix it with the inverters or DC to AC converters, which are related to power generation. Oscillators are circuits that produce a continuous signal of some type without the need of an input. These signals serve a variety of purposes: communication systems, digital systems, including computers, and it can be used in test equipment just as well. The feedback oscillator relies on a positive feedback of the output to maintain the oscillations. The relaxation oscillator makes the use of an RC timing circuit to generate a non-sinusoidal signal such as square wave. So generally speaking, oscillator would be a block that requires only DC supply voltage, and at the output we can have either sine wave or square wave or sawtooth wave as shown. Oscillators, as we said, are electronic circuits that produce a periodic or repetitive AC waveform with only the DC supply voltage connected, applied to the circuit. Since an oscillator has no external input signal connected or nor required, we have to find different ways of initiating oscillations. We usually relate name oscillator to a sine wave signal generation. A multi-vibrator is generally used name for square wave generators. Of course, in laboratory experiments we use a function or signal generator, which can generate sine, square, or triangular signals with adjustable frequency, amplitude, duty cycle, or DC offset. Basically, oscillation is a form of instability caused by feedback that regenerates or amplifies a signal that would die out due to energy losses. A feedback signal is a portion of the output voltage or current of an amplifier brought back to the input and combined with an input signal, if there is any, before processed by the amplifier. Implicitly, we introduce the concept of negative feedback in op-amp applications, which provides many beneficial features when it comes to amplifier applications, but not oscillator necessarily. Oscillators cannot operate in circuits with negative feedback, at least not intentionally. Generally speaking, a feedback concept introduces a feedback network, call it beta, which brings a portion of the output signal VO to the input. At the input mixer, designated here as M, the feedback signal is summed with the input signal. However, if the feedback signal is of opposite polarity, it is effectively subtracted from the original input signal Vs to form the input signal Vi, which is then amplified by the amplifier. This results in negative feedback, as shown in this figure below. It can be shown that overall voltage gain with the feedback, call it AF, can be expressed as VO over Vs by definition to be A over 1 plus beta A. Here, open loop gain A, being ratio V over Vs minus Vf, designates the voltage gain without a feedback, and the feedback factor or ratio beta determines the fraction of the output voltage that the feedback network is bringing back to input. Obviously, with negative feedback, the overall gain of the circuit is reduced by a factor 1 plus beta A, as can be seen from this general expression. The product of no feedback gain and feedback factor beta A is called a loop gain. So this product, beta times A, open loop gain, is called a loop gain. In general, both parameters A and B are frequency dependent, thus making the loop gain a complex number. In negative feedback, both voltage and current can be fed back to the input, either in series or parallel. Therefore, we have 4 different feedback connection types: voltage series, voltage parallel, current series, and current shunt feedback. Each of these configurations has its own advantages and disadvantages, and their application depends on goals to be achieved. Nevertheless, the most popular is voltage series configuration, such as the one illustrated in figure below, utilizing operational amplifier. In this circuit, feedback factor beta is determined by the voltage divider VF over VO, and because it's resistive voltage divider, obviously it's a ratio R2 over R1 plus R2. Now, the output voltage is given as a product of differential input voltage Vi and open loop gain. Because VR now becomes a source signal, Vs, that's a useful signal we want to amplify, minus feedback signal Vf, the ratio can be written as no feedback open loop gain times Vs minus beta Vo, because as we said, feedback voltage can be given as a product of the feedback gain beta and the output voltage. Utilizing this expression, we can find the ratio Vo over Vs, which by definition defines a voltage gain with the feedback. If we solve this previous equation by AF, you will get a value of Vo over 1 plus beta AO. In most cases, this loop gain, product actually of the feedback gain and open loop gain AO, is much higher than 1 due to the fact that AO is an extremely high number. If you neglect 1 with respect to this product, then you can simplify the expression as shown here, and canceling out VO and VO, you will get simple expression 1 over beta. If you express that as a ratio of the resistors, you find the reciprocal value of beta to be R2 plus R1 over R2. While negative feedback results in reduced overall gain, and it's defined only by the ratio of those resistors, a number of improvements are obtained. Higher input impedance, for instance, better stabilized voltage gain, improved frequency response, lower output impedance, and reduced noise with more linear operation. If positive feedback is provided around the amplifier closed loop, no input signal is required to sustain the oscillation. Even a transient disturbance like powering on the circuit or small noise voltage at the input could cause a seemingly stable amplifier to suddenly start oscillating. The stability of a feedback amplifier as a function of the frequency is determined by the magnitude of the loop gain, beta A, and the phase shift, call it phi. So if you look at the picture, you will see that we don't have any specific input signal connected to the input of an amplifier, but there is a feedback circuit. If the amplifier inverts the input signal, whatever the input signal is, and a fraction of that output voltage is brought back through the feedback, which also introduced the phase shift of 180 degrees, your signal at the output of the feedback circuit will be in phase with the original input signal. Now, if they are of the same amplitude on top of it, you have a condition of sustaining the oscillation. Now, let's say that the input signal has amplitude of 1 volt at the amplifier input. If the voltage gain is, let's say, negative 100, meaning that there is a phase shift 180 degrees, then the output will be 100 millivolts peak value, 100 millivolts amplitude, but out of phase. Now, if the feedback attenuation, which is the ratio VF over Vout, is negative 0.01, then the feedback voltage Vf becomes 1 millivolt, which is identical to Vin, same amplitude and in phase. System sustains oscillation. Here are some key aspects of the oscillator with the positive feedback. So after amplification, there will be some output voltage Vo as a product of the open loop gain and the voltage at the input of an amplifier. As soon as we have some input signal Vi, after amplification, we will get that the output voltage Vo, which is a product of the open loop gain and the voltage at the input of an amplifier. This output voltage, once again, is the input to the feedback network, which will produce feedback voltage proportional to the feedback gain and the output voltage. If this feedback signal is identical as Vi, then we have a condition for oscillation. So in order to maintain a condition that the feedback signal is equal to the input signal, loop gain must be in correct magnitude and phase. The circuit will continue operating since the feedback voltage is sufficient to drive the amplifier and feedback circuit, resulting in proper input voltage to sustain the loop operation. If we, in expression for a loop gain, substitute beta as a feedback gain as a ratio of feedback voltage over input, which is output voltage of the amplifier, and gain, by definition, is ratio output voltage over input voltage. In oscillation conditions, Vf and Vi are equal. We cancel them out, and this whole ratio becomes 1. We can now draw a general conclusion about the conditions for oscillation in a feedback oscillator. In order for a system to oscillate, the loop gain beta A must satisfy the Barkhausen criterion. The loop gain must be equal to 1. The unity gain means not only a gain magnitude of 1, but also in-phase signal reinforcement. We should always keep in mind that the amplifier and/or feedback network contain reactive components, or at least it might contain reactive components, capacitance in particular, causing the gain magnitude and phase shift to change with frequency. In general, there will be only one frequency at which the gain magnitude is unity and at which simultaneously the total phase shift is equal to 0, or multiple of 360 degrees. The system will oscillate at this frequency. Thus, designing an oscillator amounts to selecting reactive components and integrating them into circuitry in such a way that the Barkhausen conditions will be satisfied at predetermined frequency. When designing incorporates inverting amplifier, which introduces more or less constant phase shift of 180 degrees, then the feedback network has to amount additional 180 degrees shift to make total 360. In this case, the feedback signal will be in phase with the input signal and the system can sustain oscillations. So, to simplify that, we say that in feedback oscillator, a fraction of the output is returned with no net phase shift to the input. Now you might ask yourself how we can start up those oscillations. Feedback oscillators require a small disturbance, such as that generated by thermal noise, to start oscillations. This initial voltage starts the feedback process and oscillations. If you try to do the simulation of the oscillators using multisim, you will find out that it's kind of hard to do that. Computer simulations such as multisim use digital signals which do not have thermal noise. This often creates a problem for computer simulation of oscillators. Now, with respect to oscillating conditions in a circuit, we can look at the value of the loop gain and make definite conclusion what's going to happen with oscillations. For instance, if the loop gain is less than 1, then any existing oscillation in a circuit will start decreasing the amplitude, and eventually it will die out and reach 0. There will be no oscillations anymore after this transition period. If your loop gain is higher than 1, then you will start increasing the amplitude of oscillations until you reach maximum possible level of the output signal, which is usually related to a value of power supply voltage VCC. However, if you have condition that the loop gain is exactly equal to 1 and with a phase shift of 0, then you will sustain continuous oscillation with a stable amplitude. When it comes to a practical design of the oscillator with the positive feedback, RC feedback is used in various low-frequency sine wave oscillators, like the Wien bridge oscillator, the phase shift oscillator, and the twin T oscillator. And we will cover first two of those three oscillators. The feedback circuit in Wien bridge uses a lead-lag circuit, which is given below. When the R's resistance and the C capacitance have equal values, the output will be 1/3 of the input voltage at only one frequency, and the phase shift at this frequency will be 0. So if you're looking at the structure of that feedback circuitry, you will see that we have two complex impedances. Series impedance Z1 consisted of series combination R1 and reactance C1, and Z2 impedance is made of parallel combination of the resistor R2 and reactance C2. If this plot, which shows you output voltage as a function of the frequency, it clearly indicates one frequency, call it FR, for which the output voltage will be exactly 1/3 of the input voltage. This circuitry is used as a feedback circuit in Wien bridge oscillator. The basic Wien bridge oscillator shown utilizes the lead-lag network described in previous slide to select a specific frequency that is amplified. The shadowed rectangular shown here in a schematic indicates voltage divider consisted of impedance Z1 and Z2, bringing feedback voltage VF to the input. Since this is a non-inverting input of an op-amp, the amplifier operates as a non-inverting amplifier with a gain of A equals 1 plus R4 over R3. You remember RF over RI plus 1 defines the gain of a non-inverting amplifier. As we know, a non-inverting amplifier has a 0 phase shift, so the feedback network must do the same in order to keep the net loop shift to 0. If we substitute Z1 by series combination of R1 and reactance XC1 and impedance Z2 by a parallel combination of resistor R2 and reactance XC2, the feedback factors, which is a ratio of VF over Vout by definition, becomes a voltage divider ratio, and it's given with this expression. For oscillations, loop gain beta A must be equal to 1. That means it must be a real number, and the voltage gain being 1 plus R4 over R3 is a real number as well. Then beta feedback factor must be a real number too, so that the imaginary part must be 0. So obviously in this complex number, imaginary part must be 0 in order to have a loop gain of 1. if this part is equal to 0, and for simplicity, assume that R1 and R2 are equal, as well as C1 and C2, then this condition becomes R squared minus X squared to be equal to 0. From this equation, we can define frequency of oscillation, which is 1 over 2 pi RC. Of course, once again, the condition is that R1 is equal to R2 and that the C1 is equal to C2. With zero imaginary part, expression for feedback factor becomes as shown here. As you can see, there is no imaginary part, and with the assumption that R1 is equal to R2 and C1 equal to C2, this ratio simply becomes 1 over 3. Barkhausen criterion then determines required voltage gain of the non-inverting amplifier as beta equal 1 over voltage gain. From this expression, you can easily say that voltage gain must be equal to 3. Therefore, the non-inverting amplifier must have a gain of exactly 3 as set by R3 and R4 to make up for the attenuation of the feedback network. If it is less than 3, oscillations will not occur. If it's higher than 3, the sine wave will be clipped due to saturation levels. So we derived required value of voltage gain to sustain oscillations. We found that to be 3. However, to start oscillations, we need slightly more than that. Therefore, to produce the precise gain required for startup and for oscillations, the Wien bridge oscillator needs some form of automatic gain control. One popular method is shown here and uses a JFET transistor. The basic idea here is to provide a variable gain of the amplifier given with the expression 1 plus RF, this is RF, over R3 plus RD, where RD designates variable resistance of the JFET. If you compare this expression for non-inverting amplifier gain, we have 1 plus RF over Ri, and here Ri will be Rd plus R3. The key elements of the automatic gain control circuits are highlighted in yellow. The diode D1 operates as a half-wave rectifier, rectifying negative half cycles of the output voltage. When conducting, of course for negative cycles only, it provides charging current for filtering capacitor C3 up to the negative peak of the output signal. This develops negative gate bias voltage for the JFET that is related to the output level. Different VGS biasing voltages provides different resistance of the JFET channel RD. Recall from ETEC221 that a JFET acts as a variable resistor in ohmic region, as can be seen from ID versus VDS plot. For instance, when VG is equal to 0 volts, at VDS drain source voltage of 2 volts, drain current will be 5 milliamps. However, at reverse gate source voltage of VG equals negative 1 volt, you see that for the same condition VDS equals 2, we will have only 3 milliamps. It looks as if with changing the gate biasing voltage, we can alter resistance of the channel, of the JFET. So when reverse biasing voltage is 0, resistance will be small, so we will allow 5 milliamps to flow. However, if we have some negative voltage and we increase this reverse biasing voltage, we will reduce current, so it looks that we are increasing resistance of the JFET. Higher reverse voltage increases depletion region, shrinking the channel of the JFET and thus increases the resistance. Since level of reverse biasing depends on output voltage, we can establish automatic resistance control of the JFET resistance. This is a key property for automatic gain control. So how we can utilize this property in Wien bridge oscillator? If we go back to expression for amplifier gain, A equals 1 plus R4 over R3 plus RD, we can see that for lower values of RD, the gain increases and vice versa. So when output voltage is low or zero, there is no much reverse biasing. VG is approximately 0 volts. Under this condition, the JFET channel is fully open with minimum resistance RD. Say that is so low, approximately 0. This will provide a high voltage gain, higher than 3, to start up oscillations, constantly increasing amplitude of the output voltage. So when this RD is equal to 0, you will have the highest gain, which is set up in such a way to exceed value of 3, so we can start up oscillations. However, with increasing output amplitude, the reverse biasing voltage increases, causing reduction of JFET channel and therefore increasing RD. Increased RD reduces amplifier gain until fine balance has established to sustain equilibrium in which the amplitude reaches the optimum value that assures voltage gain of 3. This is called automatic voltage gain control. Here is one practical example with Wien bridge oscillators. The values of all resistors and capacitors are given, and we have to find the frequency of oscillation. This is a quite straightforward problem, and for the value of R1 and R2, which are 680 ohms, and capacitance C1 and C2 of 4.7 nanofarad, applying formula for the frequency of oscillation, we can find that it's 48.9 kilohertz. The phase shift oscillator uses 3 RC circuits in the feedback path that have a total phase shift of 180 degrees at only one frequency. Since feedback network introduces phase shift, unlike in case of Wien bridge oscillator, the amplifier itself must introduce phase shift to amount to 0 net shift around the loop. For this reason, an inverting amplifier is required for this circuit. Even with identical R's and C's, the phase shift in each RC circuit is slightly different because of the loading effects. When all R's and C's are equal, the feedback attenuates the signal by a factor of 29. If we derive expression for the feedback factor, which is a ratio VF over Vout, you can get this complex number. Now, again, to eliminate imaginary part, xc to the power 3 minus 6r squared, xc must be equal to 0. xc and xc cancels out, so you will get expression that xc squared must be equal to 6r squared, which gives us a frequency of oscillation at which this will happen as 1 over 2 pi square root of 6rc. Conditions for oscillations with the phase shift oscillator is that if all R's and C's are equal, the amplifier must have a gain of at least 29 to make up for the attenuation of a feedback circuit. This means that RF over R3 must be higher than 29, as shown from the derivation below. We said that the frequency of oscillation when imaginary part is equal to 0, our ratio VF over Vout reduces to this expression. Xc squared is equal to 6r squared, and if you substitute that value here, you will get the expression negative 1 over 29. Negative again indicates that there must be a shift of 180 degrees for the net phase shift of 0 around the loop. And one problem associated with the phase shift oscillator. In this case, it's a not analytical problem, it's designing problem where the frequency of oscillation is given 800 Hertz, and we are asked to find the values of components of the phase shift oscillator that will provide this frequency. Of course, you have to select arbitrary value of the capacitance, and in this case it's suggested to use 10 nanofarads. Once again, you apply directly expression for the frequency of oscillation, which you solve by R, and if it's required to be 800 Hertz with the capacitance of 10 nano, will give you a value of 8.12 kilo ohms. Since this is not a standard value, the closest value will be actually 8.2 kilo ohms. Now we can calculate the value of RF in this circuit, knowing that the gain must be equal to negative 29, and in this case RF must be equal to 29R. With R of 8.2 will give us 238 kilo ohms. Again, the closest value actually would be 240 kilo ohms. And this will conclude lecture 5, oscillators, first part. We will continue with the part 2.